Let's kick off with a classic Python puzzle. What's the real difference between is and equals equals? While equals equals checks if two objects have the same value, is checks if they are actually the same object in memory. Imagine you're configuring an AI model. Sometimes you want to know if two configurations are identical in content, and other times if they are literally the same instance. For example, two dictionaries with the same values are equal, but unless they reference the same memory, is will say they're different. This distinction is crucial when managing resources or debugging tricky bugs in AI pipelines. Consider this real-life AI scenario. You have two configuration dictionaries for your model, both with the same parameters. If you compare them with equals equals, Python returns true, they look the same. But if you use is, Python returns false because they occupy different places in memory. Only if you assign one variable to another, making them point to the same object, will is return true. This subtlety can prevent accidental overwrites or unintended sharing of state in AI experiments. Are Python strings immutable, and why does it matter? Immutability means once a string is created, it can't be changed. This design boosts memory efficiency and security. But there's a catch. If you concatenate strings in a loop using plus, Python creates a new string each time, leading to poor performance. In AI, when cleaning large text datasets, that can slow down preprocessing dramatically. Instead, appending to a list and joining at the end is much faster and more efficient. Imagine you're preparing text data for a large language model. If you use text plus equals word inside a loop, Python creates a new string every time, which is inefficient for big datasets. The smarter approach is to collect words in a list and use join list at the end. This way you process text in linear time, making your AI data pipeline much faster and more scalable. Python's logical operators, and or use short-circuit evaluation. This means that in an AND statement, if the first condition is false, Python doesn't bother checking the rest. In an OR statement, if the first condition is true, it stops right there. This feature protects your code from unnecessary errors like trying to access data that might not exist. In AI, it's especially useful when validating streaming data before running complex operations. Suppose you're processing a live data stream for an AI model. Before running matrix operations, you want to make sure the incoming data is valid. Using short-circuit logic, you can check if the data exists and meets your criteria in a single line. If the first check fails, Python won't risk running code that could crash your program. This keeps your AI pipeline robust and error-resistant. Range function changed significantly from Python 2 to Python 3. In Python 2, range creates a full list in memory, which can be a problem with large datasets. Python 3's range returns a lazy iterable, generating numbers on demand and using almost no memory. This is a game changer when working with massive AI datasets, allowing you to iterate over millions of items without crashing your system. Imagine you need to process 10 million images for an AI project. With Python 3's range, you can loop through all images without worrying about memory usage. In Python 2, the same operation would fill your RAM instantly, possibly crashing your computer. This small change in Python 3 makes it much more suitable for modern AI and data science workflows. Break and continue are essential tools for controlling loops in Python. Break exits the innermost loop immediately, while continue skips the rest of the current iteration and moves to the next. In AI training, you might use continue to skip a batch with bad data, or break to stop training early if your model reaches a target accuracy. Understanding these controls helps you write more efficient and readable code. Picture a nested loop for training an AI model. The outer loop runs over epochs and the inner loop processes batches. If a batch has a bad gradient, you use continue to skip it. If your model hits the target accuracy, break exits the batch loop early. These commands give you precise control over training, making your code both robust and flexible. Common Python pitfall is the mutable default argument bug. Default arguments are evaluated only once when the function is defined, not each time it's called. If you use a mutable object like a list as a default, all calls share the same list. This can lead to unexpected behavior, especially in AI experiments where you might be collecting metrics across runs. Always use none as the default and create a new list inside the function if needed. Suppose you're collecting evaluation metrics in an AI experiment. If you define a function with a default list argument, every call adds to the same list, mixing up results from different runs. This can make debugging a nightmare. The safe way is to default to none and initialize a new list inside the function. This ensures each run gets its own clean slate. Tuples are faster and safer than lists for storing fixed data like geometric coordinates. Tuples are immutable and stored in a single, contiguous block of memory, making them more efficient. They're also hashable, so you can use them as dictionary keys. In AI, this is perfect for storing bounding box coordinates and object detection. Tuples guarantee the data won't change unexpectedly. In building an object detection pipeline, you often store pixel coordinates for bounding boxes. Using tuples ensures these coordinates stay fixed throughout the process. Plus, you can map each bounding box to a unique label in a dictionary thanks to tuple hashability. This prevents accidental changes and keeps your AI pipeline reliable. Python dictionaries are incredibly fast, even with millions of keys. But what happens if two keys hash to the same index? Python uses open addressing with pseudorandom probing to resolve collisions. It calculates a new index until it finds an empty slot. This keeps lookups fast, which is vital when building large AI vocabulary maps for NLP tasks. Imagine mapping millions of unique words to token IDs in a natural language processing project. Python's dictionary handles this efficiently, even with hash collisions. The underlying algorithm ensures that lookups remain at lightning speed, making large-scale AI text processing practical and scalable. When should you use a set instead of a list? Sets are perfect for maintaining unique items and performing fast membership tests. Checking if an item is in a set takes constant time, while lists require scanning each element. In AI, this is crucial when building vocabularies or filtering out stop words from massive datasets. Suppose you have a dataset with 50 million words and need to filter out common stop words. Storing stop words in a set lets you check membership in microseconds, making preprocessing much faster. Lists would slow you down, especially at this scale. Sets are the go-to choice for efficient AI data cleaning. Python's args and asterisk quargs let you write flexible functions that accept any number of positional or keyword arguments. Args collects extra positional arguments as a tuple, while asterisk quargs collects keyword arguments as a dictionary. This is especially useful in AI, where model configurations can vary widely between experiments. When designing a machine learning model trainer, you might want to accept different hyperparameters for each model. Using args and asterisk quargs, you can pass any configuration without changing your function signature. This makes your code adaptable and ready for any AI experiment. Copying objects in Python can be tricky. A shallow copy creates a new collection, but its elements still reference the original objects. A deep copy, on the other hand, recursively copies everything, so changes in the copy don't affect the original. This is vital when cloning complex AI model configurations to avoid unexpected side effects. Suppose you have a nested dictionary for a neural network's architecture. If you use a shallow copy, changes to inner lists affect both the original and the copy. With a deep copy, you get a completely independent clone, so you can safely tweak parameters for experiments without risk. Python's try except else finally block gives you fine-grained control over error handling. The try block runs risky code. If an exception occurs, except handles it. If no errors happen, else runs. Finally always executes, perfect for cleanup. This structure is essential for robust AI pipelines, especially when downloading or processing large datasets. Imagine downloading batches of images for AI training. You wrap the download in a try block. If a timeout occurs, accept logs the missing URL. If the download succeeds, else saves the image. Finally, you update the progress bar, ensuring your UI always reflects the latest state. This pattern keeps your workflow smooth and error-tolerant. Generators are special functions that yield values one at a time, pausing after each yield. They only keep one item in memory, making them perfect for processing big data. In AI, generators let you stream massive datasets like video frames without running out of RAM. This is a must-know for efficient data pipelines. Suppose you're feeding a 50 GB video dataset to a computer vision model. Loading it all at once would crash your system. With a generator, you load and process one frame at a time, keeping memory usage minimal. This approach makes large-scale AI training feasible on standard hardware. Python distinguishes between syntax errors and exceptions. Syntax errors are caught before your code runs, they break language rules. Exceptions happen at runtime when the code is valid but something goes wrong, like dividing by 0. Knowing the difference helps you debug faster and write more reliable AI code. For example, writing if equals 5 is a syntax error, Python won't even run it. But accuracy equals correct predictions / total images can throw a 0 division error if total images is 0. Handling both types of errors is crucial for building robust AI systems that don't crash unexpectedly. Switching gears to collaboration tools, git fetch and git pull are both used to update your local repository from a remote one. Git fetch downloads new commits and branches but doesn't change your working files. Git pull does a fetch and then merges the changes into your current branch, updating your files automatically. Knowing when to use each helps you avoid accidental overwrites. Imagine your teammate pushes a new model weight file to the main branch. Running git fetch lets you review their changes before merging. If you run git pull, your local files update instantly. This workflow keeps your AI project organized and prevents losing your own work. Merge conflict happens when two developers change the same lines of code in the same file on different branches. Git can't decide which version to keep, so it marks the conflict for you to resolve. This is common in AI teams working on shared codebases, especially when tuning model parameters. Suppose you set the batch size to 64 in train, pi, while your teammate set it to 32 on the same line. Git will stop the merge and insert conflict markers. You must manually choose the correct value, remove the markers, and commit the resolved file. This process ensures your AI code stays consistent and functional. Is a special file that tells Git which files or directories to ignore. For AI projects, you should never commit large raw datasets, model weights, or sensitive API keys. Including these in gitignore keeps your repository clean and secure and prevents accidental uploads of huge or private files. In a typical AI project, your gitignore might include folders like data raw, models, checkpoints, env files, and pycache directories. This ensures that only code and essential configuration files are tracked, making collaboration smoother and reducing the risk of sharing confidential information. A detached head state in Git happens when you check out a specific commit instead of a branch. You're looking at a snapshot in time, and any new commits won't belong to any branch. They can easily get lost. This is risky if you're experimenting with old versions of your AI code. Suppose you want to test code from 2 weeks ago to debug a drop in model accuracy. You check out an old commit, entering detached head state. To keep your changes, immediately create a new branch from there. This way your work is safely tracked and won't disappear. Git reset comes in two flavors, soft and hard. A soft reset undoes your commits but keeps your code changes in the staging area. A hard reset wipes out your commits and code changes, reverting your files to a previous state. Use hard reset with caution, as uncommitted work will be lost forever. If you want to undo recent commits but keep your code, use a soft reset. If you need to completely revert your project to a previous state, use a hard reset. Always double-check before running a hard reset, especially in collaborative AI projects, to avoid losing important work. We've covered the most important Python fundamentals for AI, from understanding object identity and string immutability to mastering loops, data structures, and error handling. Each concept is not just theory but directly impacts the efficiency, reliability, and scalability of your AI projects. On the collaboration side, tools like Git and GitHub are essential for team-based AI development. Understanding fetch, pull, merge conflicts, git ignore, and reset commands helps you work smoothly with others, protect your code, and recover from mistakes. All these Python and Git fundamentals come together in real-world AI projects. Whether you're preprocessing data, training models, or collaborating with a team, these concepts ensure your workflow is efficient and your results are reproducible. By mastering these basics, you avoid common pitfalls like memory leaks, slow code, and lost work. You also gain the confidence to tackle larger, more complex AI challenges, knowing your foundation is solid. As your AI projects grow, these Python and Git skills become even more valuable. Efficient data handling, robust error management, and smooth collaboration are the keys to scaling up from small experiments to production-level systems. Python and Git are constantly evolving, and so should your skills. Stay curious, keep experimenting, and always look for ways to improve your workflow. The AI field moves fast, but a strong foundation will keep you ahead. With these core concepts under your belt, you're ready to tackle real AI projects with confidence. From writing efficient Python code to collaborating seamlessly with your team, you're set up for success in the fast-paced world of artificial intelligence.